In this video, we will look at the structure of enhancement type MOSFETs. This structure is a lot simpler when compared to the bipolar junction transistor. The main part of the MOSFET structure is a capacitor. The substrate is a p-type semiconductor, which is a conductor. In the middle, we have a thin layer of silicon dioxide, which is a perfect insulator like glass. And on top of it, we have the gate terminal of the device, which is a good conductor. The gate plate is made of polysilicon. This is the material used at the time I'm recording this video, and it may change in future due to the improvement of technology. Now you may ask, why do we call these components MOSFET? MOS stands for metal oxide, but polysilicon is not a metal. This naming convention was remained by the first generation of MOSFETs with the gate material of aluminum. To study how the current flows in a MOSFET, let's start from the beginning. Let's assume that we have a p-type silicon wafer or substrate that provides the physical support for our transistor. We add a thin layer of a good insulator such as silicon dioxide on top of the substrate, and on top of this insulator, the gate electrode is placed. As I mentioned earlier, the gate material is polysilicon, which is a good conductor. The substrate is also a conductor, so our silicon dioxide insulator is a dielectric that is sandwiched between gate and substrate conductors. Therefore, we can find the capacitance between these plates. Epsilon is the permittivity of the medium between plates or dielectric constant. A is the area of each plate, and d is the distance between the plates. We indicate the oxide thickness, which is the distance between the two conductor plates, by Tox, which stands for the oxide thickness. Now let's see what happens if we apply a potential difference between the capacitor plates. If we apply voltage Vg such that the positive terminal is connected to the gate and the negative terminal is connected to the substrate, positive charge is accumulated on the top plate. From the first part of this course, you already know that in the substrate, which is a p-type semiconductor, holes are the majority carriers and electrons are the minority carriers. The positive charge of the top plate attracts electrons to its surface. We call these accumulated electrons near the surface channel. So by applying a sufficient positive voltage to the gate, we have created a channel of electrons near the surface. This channel is a good conductive path. We can control the conductivity of this channel by changing the voltage Vg and the oxide thickness. Generally, we reduce the oxide thickness as much as possible to have the maximum capacitance and control the channel by changing the Vg voltage. We created the channel, but there is no flow of electrons and the MOSFET is off. To create a current flow, we can apply a voltage difference between the two ends of the channel. In this case, we can create a mobile charge, and current will flow through the circuit. We can control the current of the channel by changing the gate voltage. So we have created a voltage-controlled current source. In practice, the substrate is a large area and millions or billions of transistors are created on this area. So to apply the external voltage across the channel, two heavily doped N-type regions are created across the channel. Since these areas are heavily doped N-type semiconductors, we can easily attach metal contacts to them. Keep in mind that if we directly connect metal to the substrate, it will not create a good ohmic contact. We name one of these N+ regions source and the other one drain. We also create a heavily doped p-type region for the metal contact of the substrate. In this scenario, all of the metal contacts are on the top surface of the silicon wafer. This is how MOSFETs are made in practice. If you look at the physical structure of the MOSFET, you will quickly understand that the MOS structure is symmetrical. If you remember, in BJTs, we couldn't change the emitter and collector terminals. In the MOS structure, drain and source terminals are interchangeable. You have to keep in mind that a MOSFET has 4 terminals. In many applications, we don't care about the substrate, so you can change drain and source terminals because, as mentioned before, the device is symmetrical. However, there are times that one of these terminals is connected to the substrate. In this case, the terminal that is connected to the substrate is the source, and the other one is the drain. Therefore, in this case, we cannot change the source and drain terminals, and the terminal that is connected to the substrate is always the source.